Sure. We have an over 6. I'm using a smaller chart, so if you see that I'm starting to write too small, tell me and I'll start writing bigger. So, yeah, it was due October 5, so I postponed it to October 12. We're going a little slow since last class. There's midterm 2. I think the suggestion is to make it Thursday, the following Thursday after October 29. So this was the proposed date. Suggestion is when will this be? So
The 4th, November 4th.
November 4th. And that's Thursday, right? Yes. So question mark, because not all of you guys, or we need to still find out from John. Right? Yeah. So we talked about conservative forces, and the whole idea was bringing that up was that so that we can do something similar in analytic function. So remember what are the things we talked about in conservative forces. He said there is a work, first we define that work done for a work done by a force to move a particle from our initial or final. Maybe the language should be rephrased. The work done while the particle is moving from our initial to our final. It need not be that this work is what is actually making it do. While the particle is going from initial to final, work done by a particular force is defined as dl dot product of the force and the displacement that builds on the whole path. And of course, when you go from initial to final in 3-dimensional space, this is a path dependent quantity. In general, this is a path dependent quantity. So a conservative force is an idea based on this work done. So there are 3 properties which one implies the other. One is that the work done by the force is path independent. The second is that so immediately if you say that this is path independent, that means I can go from initial to final along one path, and while coming back final to initial, I can come back by the other path, and that means to say that the loop integral along a closed path of work done is 0. which seems to suggest that if that's equal to 0, del cross F has to be equal to 0. That's using the Stokes theorem. And so this is equal to 0. Or just the fact that if it is path independent, it depends only on the initial and final points. That means this must be a total derivative, right? The force must be a total derivative. And then you say that that also suggests that the force can be written as a gradient of a scalar function. And that's called the potential energy. And it's the negative of that just for notational purpose. That's how one defined it. So where U is the potential energy. So if not for the force being conservative, there is no potential energy. That's why we always talk about gravitational potential energy, electric potential energy. We never talk about potential energy associated with normal force or the force due to friction. Each of this implies the other. And yes, and in fact, one can imply the other one also. Either one of them. So Johnny, we were talking about midterm 3. Sorry, not midterm 3, right? Midterm 2, yeah. And apparently we were thinking of changing it to November 4, which seems to be convenient, and that's a Thursday. And at 5 p.m. Does that suit you?
Yeah.
Sure.
Yeah. Thursday is no issue.
Thursday 5 p.m. Okay.
Yeah.
And Ken and Rob, you guys stop. So, okay, so let's fix this. Yeah, so let's fix this to 5 p.m. Write it for myself. Tuesday and Thursday. Thursday. Right. So there's no class on that day, right? Okay.
Yeah.
So, yeah, okay. Okay. So that's the 3 properties of a conservative force, and we discussed this last time we had a discussion on this pretty much in detail. The idea is that can we do something similar in analytic function, and let's talk about that. So let's see. Let's begin by so we're talking about complex functions. So let's say you have z is equal to x plus iy, right? And let's also introduce z star. That's x minus iy. So that's your 2 variables associated with x and y. If you have a function, a complex function, x comma y, this can be written as u of x comma y, I times d of x comma y. And f star, of course, is, and these are real. And yeah, so first let's see if we would like to write this in terms of z and z prime. So let's make some transformations associated with that. So immediately let's solve for x. So x is equal to, if we add this z plus s star, so it is 1 by 2 z plus 1 by 2 z star. So that should be fine. So y similarly is divided, right? So it's 1 over 2i z minus 1 over 2i. Sure, that should be clear. We would like to talk about derivatives. Let's talk about derivative with respect to z and derivative with respect to z prime. So I do it here. I think that it's fixed. So, so if I have derivative with respect to z, yeah, that means that derivative with respect to x is equal to z by x. Is that correct? Yes. Yes. Sure. This should be itself correct. And dz by dx using this equation is 1. dz star over dx is 1. So that's nothing but d by dz plus d by dz star. Similarly, derivative with respect to y is dz to dy. And z with respect to y is I. Z star with respect to y is minus I. So that's I times z. We did this last time also. Right? This part alone we did. But now I would like to see what is derivative with respect to z. Let's also do that. So d by dz is equal to, first let me multiply by I. So that makes it a minus, and I subtract out. So this is d by dx. That's correct. So we do a minus I, that makes it a plus. So I'm adding minus I, so it's a minus, so it subtracts out. And probably a 2. So I'm just adding these two equation and this combination. And the same thing with d by dz star. For that, I want to subtract this out, so I'll multiply by an I and then add. Right. So it's d by dx plus so multiply by 9 and okay, is that right? Okay, so that's good. So you have f is equal to u plus v. So let's now what is derivative with z and derivative with z prime? So, let's see what is d by dz f, right? That's here. It's equal to 1 by 2 x minus I by 2 y times u plus. So expand this out, so there are 4 pieces in here. So that's 1 by 2 by 2x. Then there is I and I minus plus I times 1 by 2. Let me know if I'm making any errors. It's algebra at this point, but after this step. Similarly, d by dz star in principle, this can also exist, and in general, for any complex function, we have 1 by 2 x plus I by 2. And that is equal to 1 by 2 times x. And this is now minus d by dy. So that's just if this exists, like in general, if I want to write derivatives of f instead of x and y, if I'm writing it in terms of z and z star, that's your two definitions. But analytic function now, so let's say this is a general function. So analytic function, as we talked for a week now, is when d by dz exists, first condition is that d by dx star times f is equal to 0. If that's equal to 0, what is the necessity? This is equal to 0, and that's equal to 0. And what are those? If you remember, those are nothing but the Cauchy Riemann conditions, right? So this implies immediately that du by x minus dv by dy is equal to 0, and du by dy x is equal to 0. So that's your Cauchy Riemann. If that is true, we can go back and rewrite our derivative with respect to z in various forms. We can substitute whatever we want. And now, since there is no z star dependence, it's okay to say that it's a total derivative. If there are two variables, actually I should be careful here. Let me say this is d by dz star. Because f is a function of z and z star in general, but I'm saying it does not depend on z star. If it does not depend on z star, there's only one variable left. So that's a total derivative. So partial derivative is the same as total derivative. This, of course, is equal to this whole expression. But if I use this in this place, so this is dv by dy is the same as du by dx, right? So this is du by dx. If I replace dv with that, and if I replace dv by dx with minus du, so it's minus I du by dy, which is the same as u is there d by dx minus I by 2. I think we had it here, d by dx minus I y by 2. So that's d by dz of u, right? So it's 1 by 2 partial derivative of z with respect to u. So that's one way of evaluating that. It is also equal to, I didn't have to replace u. Instead, if I had replaced, or instead of replacing v, if I had replaced u, I would have got dv by dy. So then dv by dy and du by dy would have been minus minus, which becomes plus. That's plus I dv by x. And again, if I had taken out that, if I take out the I, there is a minus I remaining. So it is, again, this is also equal to 1 by 2 d by dz of v. That's another way of writing it. But I can also, instead of replacing both v and u's, replace the v here, replace the u there, right? So then you can get more expressions. So this will stay du by dx, right? And this one will stay plus I dv by dx. But then u plus iv shows up. And did I do this correct? Yeah, I think so. So this is d by dx of f, right? You want, because u plus iv is f. Is that right? You seem to be not happy.
Last one. Yeah, this one.
This is not correct.
And
I replaced v.
mhm,
So this is this one, right? This piece.
mhm.
That's here. And instead of writing it this one, I wrote it this way
Okay.
because these two are the same, right?
Mhm. Yeah, good.
So then d by dx comes out common, right? And u plus iv is f.
Good.
Same thing I can do with dv now. So this is dv by dy plus minus I d by dy of u. So this time I pull out a minus I. Oh, sorry, this is dy. So dy. What is this? Y? Yeah, this is d by dy. So take a minus I out. So this is minus I d by dy. Various ways of writing. Like if you know the analytic, if you know that this function is analytic, instead of taking the derivative with z, you can do any of this, and that's works out. Okay. And again, the important piece is this, that an analytic function means it is. It is sometimes a good idea to have an analogy between this part and something related with conservative forces, and conservative forces where a curl of the force is equal to 0, the force is equal to negative gradient of u, and this path integral shows up very clearly in electrostatics. Right, so one would think that there should be a one-to-one relation there, and there is. So let me hint onto that. So, or let me come back to that later, because first I should show that this is path independent, right? So first let me show the path independent part and then come back to this. So first let's show that if there is an analytic function which is independent of z star, that means it will imply that there is a path independent. So we'll start from here, this equation, and show that if you do an integral along on a complex plane, then it will be independent of the path. So let's do that. So let's define an integral, or first let's say this is the partial derivative. The partial derivative of z star with respect to f is equal to 0. Okay. And let's see what we can do about that. that immediately tells us if something is equal to 0 at one point or many points, I can sum up all those zeros and that should still be 0, right? So let's say I do an integral on a complex plane, z. Let me check, is this the argument I want to use with this last week? Yeah. Okay, yeah, I think that's what I want to do. Okay, so let's say, yeah. So there is a complex plane, let's see x, and let's see y, and this is your complex plane z, x is a real part. And let's have some surface in the sense, some region that we are integrating on. And the moment you have an integral, region, I can actually break it into small rectangular pieces, right? So let's make this a special region. Which has this feature that this is x comma y, that one corner is x comma y, and let's say x1 y1, and this is x2 y1, and this is x2 y2, and this is x1. That's it. So we are integrating on a rectangular region, let's say. So that would mean that so we say that this is this region is being integrated on this part here. One could have done this for any region, but I'm taking it specifically for a rectangle so that it is easier to evaluate. So that's dx, and that's dy on that rectangular region, and we say this is dy star f is equal to 0. So we are saying this is an analytic function everywhere on that region. So for an analytic function, if a point it is analytic at one point, then if you add up all the zeros, that should be equal to 0 still. Right? So that's a idea. This immediately brings in this piece here. So let's put that in. So we have x1, x2, x, y, y1, y2, and we have 1 by 2. So I think 1 by 2 is there on both sides. So it's both terms. That's d by u by dx minus of dv dy I. This whole thing should be equal to 0. Again, it is clear that it should be 0 because these are Cauchy-Riemann conditions. If it is analytic, this should be equal to 0. That should be equal to 0. So if something is equal to 0 in a region, it will be the sum of them will equal to 0. This statement I'm making that if something is equal to 0 in a region, then it should be the sum of all those points should be equal to 0. Does not always work. When does it not work? So if I have, let's think of it like this. So I have a function. Right? So I integrate it from x1 to x2. So this is a function, one single variable function. And I have an integral, the x, f of x is equal to, let's say, or if, let's say a, right? If I tell you that x1 to x2, right? If f of x is equal to 0, everywhere from between x1 to x2, then does it imply that a is equal to 0?
Dirac delta function.
Yes, that's correct. Sometimes you have to be careful, like, so the whole point is f of x is 0 at every point. That's okay, but what if, maybe I should add a statement, what if it is not 0 at one point, like just barely at one point, and you would again argue that in pure mathematics, the way we define a function, if I remove a point, that should not affect the area because one point has no area, right? A line does not have an area. But the whole point is that if that point goes to infinity, then that can contribute, and infinity times 0 is a possibility. Is that clear? You see that in electrodynamics, that plays a crucial role because where the point charge is there is too much electric field in there. So we are avoiding those discussions here, right? We are actually saying that these are all fine. If it is not analytic at a point here in between, then all those issues comes in. So if there is a charge, that would mean that there is one point where this is not analytic, and we'll talk about that. That is where that will be called a pole. Maybe if you have seen complex analysis before, it will lead to the idea of a pole. But as of now, there is no, it's analytic everywhere in that region. Okay. If it is analytic everywhere in the region, this is a derivative. That means integral of a derivative cancels out, right? Integral and derivative are inverse of each other. So one of the integral goes away in this. So let's have 1/2 goes away. Let me take the first term, that is surely a dy. Right, so there is a dy going from y1 to y2. And when I do the integral in x, I get u of x comma of x2, right? U of x2 comma y minus of u of x1 comma y. Is that clear? So that's the first term here. That's this term I have taken care of, the first term. The second term, let me write it here so that I have space. Second term is minus, and 1/2 I have killed it because it is equal to 0, right? So it's relevant. Derivative of y goes away, so x remains. So x1 to x2, and you have v of x integral still remains, so y2, v y2 minus. Is that clear? Like his argument here that I'm integrating and differentiating or integration and differentiation is inverse of each other, so it survives only on the boundary. So it is plus I, 2 more terms. Now y is gone, so the x remains. U. Finally, I y2. Okay. Okay, so what does that integral mean? Okay, so first let's look at this. We are integrating on y. keeping x fixed. Right? We're integrating on y, keeping x fixed to x2. X is fixed, and we are integrating from y1 to y2. That's this region. Right? That's along that line. Let me give some labels here. Let me call this C1. This is C2. Let's say that's C3, C4. That's the path I'm choosing. Right? And this will, if I'm going only along this line, that means I'm integrating on that line. That's what it means. So this first integral here means that I'm going from y1 to y2, keeping x2 fixed. That means I'm integrating on C2. So I'm integrating along the contour C2. So the path will be called a contour. So this path of, I think, and there's the path is the same as contour. So that will be a notation we will start using. Like earlier in work done, we said path. Here it's a two-dimensional plane. This will be called a contour. So this is the same as integrating on the contour in the direction that I give there. So that's integrating dy of u. And now I don't have to specify whether it is x2 or y because C2 decides that. Right? C2 tells me that fix x2 and integrate on y. Right? So all this information that x2 comma y and all that is there inside that information that it is contour C2. Now next comes minus of keep x1 fixed and go from y1 to y2. Keep x1 fixed, go from y1 to y2. But that's opposite to the contour that I showed in C4. But then I can flick the sign and that gives me the same as this. So if I write it as plus of C4, that's good. Is that clear? So this is plus of C4 of the y of u. Next one, minus of v, keep y2 fixed. So y2 is fixed, and I go from x1 to x2. So that's, and it's minus, so it is plus C3. And then there is integrate along x, keeping y1 fixed, go from x1 to x2, and it is plus, so it is plus C1. Keep doing that for other terms also. So it is plus I times dx. Keep y2 fixed and go from x1 to x2, x1 to x2, keeping y2 fixed, x1 to x2, keeping y2 fixed is minus C3 of course. That's what it is. Maybe, yeah. Okay, we'll see. Okay, minus I C3. Yeah, might be okay. Yeah, minus I dx. U next one is keep y1 fixed. Keep y1 fixed, go from x1 to x2. This is minus I C1. And finally, it is keep x2 fixed. Keep x2 fixed, go from y1 to x, so that's C2. That will finally keep x1 fixed, go from y1 to y2, we're going in opposite direction, so it's plus I C4. Okay, hopefully that's clear. Okay, one more thing, we would like to talk in terms of z, right? We're talking in terms of x and y. You're actually going in the z plane. So let's make one more observation. I should have kept this. Okay. Notice that along C1, the y is equal to 0. If I'm going along C1, I'm changing dx, but I'm never going up, right? So that all the elements along y is equal to 0.
Mhm.
So as well say I times dy is equal to 0. That means dz is equal to dx plus I dy. That's simply dx. Right? Only along C1, not along any other path. If I'm going on C1, dz, which is in general dx plus I dy, is simply dx itself, because dy is equal to 0 on that path, on that particular, only on C1. You're going completely on the x-axis. All the movement is on the x-axis. That clear? Yes.
So that's for C3 too, though, right?
That's for C3 too. Correct. Correct. So that's C2. You want to write C3 first. So you would say again dy is equal to 0, which means I dy is also 0. So dz is equal to x plus. Oh, sorry, dx. Okay. Okay. Good. And C2 dx is equal to 0, and the x dz is equal to dx plus I dy in general. And that's simply equal to dz is I times dy. As an I factor there, that's the i's that is showing up there whenever there is x or y. Hopefully, all this should come together properly. And this is again dx is equal to 0. So dz is equal to x plus y. Okay. If I were to put all this things in that equation, I get C2 dx. Oh, now dx is the same as dy. C2, right? C2 is dx is I dy. So dy, I want to put a minus I, right? It's minus I, and that I, so that's dz. That's u. Starting from the last equation. Same thing here, minus I C4 dz. Is there a better way of doing this? Okay, maybe I should first combine it, right? There's a u plus iv there. Yeah, first let me combine this. Instead of doing this first, because then I have to deal with only 4 terms. So let me do C2 dy u plus iv. So that's C2, and then this is these 2 terms taken care of. C1 is, if I have minus I plus I, so it's minus I dx u plus iv, and that takes care of these 2. C1 done, C2 done, C3. C3 is these 2 dx, again minus I dx, minus I x. I can write this. I was doing C1 first, and now it is C3. And finally, C4 is dy u plus iv. Okay. Next, dy is the same as minus I C2 dz. This is u plus iv, and now I can take, yeah, if you allow me to do this like this, so it's minus I x C1 minus I x C3 and minus I y 4. Sorry, hold on. So yeah, no, did I do this correct? Yeah, minus I, this is dc. But I can also replace dx is the same as dz itself. So this whole thing reads minus I C1 plus C2 plus C3 plus C4 and dz of u plus iv, which is f, right? So that's very clear. Any questions? C1 plus C2 plus C3 plus C4 is a loop, so a minus I can go away. So we've shown that on this rectangular loop, z so the loop integral along the piece along that for an analytic function is equal to 0. Yes.
So those are supposed to be dz. The dx.
This can be dz. Dx is the same as dz, right? Yes.
Right. Okay.
So this is the same as dz. I should have replaced it right here.
No. And the u plus iv. Was there a reason you wanted to keep that form?
No, you can replace it here, f right here. So that's perfectly fine. Yeah. I got some stage here to replace it. Notice again, what we have done is that we started from the point that d by dz star of f is equal to 0. That means Cauchy Riemann conditions are satisfied, and we are saying that this is analytic. If the function is analytic, if the function is analytic, that means this is satisfied everywhere in a region, then this implies that the boundary of that region. One has to be careful.
I'm sorry, could you say that again?
Yeah, so if you have, so for example, let's say this is a region. If this is satisfied at every point in this region, right, that means this is equal to 0. Then I add up all those points on this, so that's an integral, which means that on the surface, now forget the region, this is also 0 on the surface alone. So which means to say that everything inside cancel away. Like this is equivalent, and one should compare this with if you're doing an integral from x1 to x2. And if there is, so this is a function f, df by dx of x, right? x1 to x2 is equal to 0. Right? What can you say? What does this imply?
Closed loop.
No. If I tell you that this is equal to 0, what can you say? There's some conclusion you can make right after this about the function.
It doesn't change with x.
No. That's correct, that if it's a constant, then this is 0. That's a special case.
Okay.
Correct. But there is a more general statement you can make. So this cancels out, right? Now do the integral.
Depend on the endpoints only.
Yes, and then
Those are equal.
those are equal, right? It depends only on the endpoints. So this is f of x2 minus f of x1 has to be equal to 0. So that means f of x2 has to be equal to f of x1. If integral is the opposite of derivative, and this you do this area, then this function, and if it comes out to be 0, then it better be the same at the 2 points we are talking about. Here now it is more general, the boundary is on a surface. When you have 2 points, 2 quantities adding up to 0, one has to be the negative of the other. Here what we are saying is that the sum of all these points on that boundary has to add up to 0. That's the best we can say. Right? That's all, and that's a generalization of that into 2 dimensions. This is basically the Stokes theorem. Stokes theorem is the opposite. You start from here and then conclude that, right? I reversed the steps, the whole thing, that way it is more logical. This is where we were. We know what an analytic function is. If an analytic function is analytic everywhere, it's important that it is analytic everywhere. And we will next talk about what if it is not analytic at one point. And then that's an additional feature that will bring in. That will be the analog of a charge. Okay. Any questions, comments on this?
Yeah, usually, we're not going to have like a perfect square, right?
Oh, yes. So what about, I wanted to add on to that. This is, seems like this is a special property of a square. Take any general path here or a region. I can always break it into square pieces. And in the infinitesimal region, I will always have a square, right? So this piece, we're talking about this piece. I can keep breaking this into square pieces, and in the small limit, every region is made up of squares.
Okay.
So if I can prove this for a square, it is true for everywhere. So that additional statement had to be made. So here it was for a square. So this is for a square, but then that implies for any part. So make that argument that you always break a region into squares and build it. It's the same thing like in one dimensional we do. We break this into rectangular pieces, right? Then there is this tiny piece that you lose every time. But in that infinitesimal limit, that's contribution is 0. So that same argument is going on here, that in that you will say, oh, what about that boundary? It is not perfect square, but those are all zeros in the limit. In the extreme limit, they will all not contribute. So they will all cancel out. And compare this with, yeah, so extra credit, right? Compare this with Stokes' theorem. The derivation goes exactly the same as Stokes' theorem in 3-dimensional space now. And the derivation is pretty much the same. It happens in 3 dimensions, but then you're working in a plane, right? Stokes' theorem is for a surface to a line integral. Exactly the same, except it is opposite. You start from this to be equal to 0 and then show that it's instead of analytic. Oh, by the way, Stokes' theorem is, Stokes' theorem says that think of the magnetic field, dl dotted with B, this is the Ampere's law, this is equal to 0. So then this can be then a surface and there's a curve of the mesh. So that's how it goes in Stokes' theorem. So at least as far as ideas go, it is exactly the same. There's one more point that is relevant in this, is that this was all true for, even though you said, oh, this is a square, is it really true for the other way? What about if it is done in the opposite sense? Like what if I had gone in the counterclockwise sense than the clockwise? In principle, it should not, but the way I have done it, it is sensitive to the direction. It is like your right-handed system. It doesn't matter whether you go use a right-handed or a left-handed system, but we always use a right-handed system. So all our conclusions are right-hand dependent, like x cross y, x hat cross with y hat is equal to z hat. That need not have been true. It could have been x hat crossed with y hat is minus z hat also, but we choose stuff, right? Yeah. So all the theorems that we, especially anything that depends on the cross product, depends on that. So similarly in here, whenever we will talk about a contour being equal to 0, we will assume that it is a counterclockwise sense of the contour. Otherwise, you have to put in a negative sign. So it is sensitive to the direction of the contour. Okay, so that's the 2 points. One is that square going to a general and the sense of rotation. Okay, with that, so now that we have, and by the way, this is called the Cauchy's theorem. And this is like the you can say Newton's law of complex function. Everything comes out of it. In fact, you reverse it like in Newton, when you're doing physics, there is Newton's law and then there is energy conservation. Right? Then you say Newton's law is more, at least when we are teaching it, one is considered more fundamental and the other can be derived. Similarly, even though I derived the analytic function, property of analytic function and then got into this, but this will be more fundamental, like whenever you want to do anything further, start from here and everything can be gotten. That's the general rule. So basically the idea is of an analytic function, but this becomes more central in the studies that or in literature that's more central. Okay, so now we have an analytic function, and I said that, oh, I wanted to give a comparison, right? An analogy between electrostatics and complex functions. So we have electric potential, right? So in electrostatic, we have phi, right? So this is electric potential. Potential, let me not say electric, so this is potential. Then we have gradient of phi, which is the electric field. So let me write it there. Electric field. This is negative gradient phi. This is the field. If I multiply by the charge, that's your energy, that's your force. Right? And next one is charge, right? Charge distribution, charge density, charge density. This is, what is this equal to in terms of the electric field? Charge density is equal to? Laplacian, that's correct, del dot E, right? Maxwell's equation. That's dotted with E, and let me put an epsilon naught in between. Otherwise, you'll put it on the right side. Right. Okay, so that's your Maxwell's equation. If you're in two-dimensional analytic function, like there is a function f, right, and that's equal to, let me write this in terms of phi 1 plus I phi 2. Now, whenever you have an analytic function, either the real or the imaginary, either one of them, okay, is a potential. Any analytic function, this is a very big statement, any analytic function corresponds to an electric potential due to it doesn't have to be a charge distribution. So remember, even if you have a continuous charge distribution, that's possible. So it's usually a continuous charge distribution. And phi 2 is another one, another charge distribution. So these are called conjugate functions. Conjugate. And of course, then the f by dz is your electric field, right? So let's say it is V1 plus IE2. Right? In fact, it works out that this is related to this, and that's related to this. Okay. So it turns out that the electric field E2 corresponding to phi 2 is exactly the electric field due to that if you calculate that. So that's kind of interesting feature in that.
So I mean, the direction you gave me, that those are equal or corresponds? I mean,
Corresponds to, like, one should think of this as electric field lines. Can you see this? Okay. Oh yeah, we can see this. Oh, there is a, yeah, we said this, right? Let's see. We said df by dz is equal to du by dz, right? Du by dz. Like if it is an analytic function, one of the relations that we wrote was 1/2 times that. Did we get that? Was it this? In the first product.
yeah, 1 by du by dz.
1/2 du by dz, right? And this is also equal to minus I minus 2I. Oh, so that's not 1/2, 2 times that, right? And 2I d by dz. And and that is also equal to du by dx, right? If it is electric field, right? Let's see. I want to show that this is the electric field, right? So there is yeah, if I were to think of this as an electric field, like if this was the potential, like this will be du by dx and du by dy, right? That's your electric field. If you were to think of this as a potential, then this is your electric field, du by dx and du by dy, which has pieces inside this. So that is your analytic function. So that's the idea that the derivative of that is equal to your potential. Did I answer the question?
Yeah.
Oh, yeah. Okay.
Okay.
Yeah. And then comes this, right? What about the charge density? Now, if a function is analytic, the derivative of that function is also analytic. Okay, so that can be taken as a homework example. That's not always, it's not obvious, but one can show that if the function is analytic, the derivative of that function, again, make that as a quiz. Remember, we had a homework problem which said that if you have a function f and you have a function g of z, if g is analytic, f is analytic, then f of g is analytic, correct? Similarly, one can show that if f is an analytic function, then the derivative of f is also an analytic function. Take that as a quiz and take that as an important quiz so that I can basically ask that in your exam, right? That's something that I can ask. Okay. If that is analytic, that means that d by dz's char of df by dz, what is that equal to? If this is analytic, what can I say about the derivative with respect to char? Zero, correct? And that's the analog with this. Unless this is not analytic in a region, this will be equal to zero, right? Similarly, this is equal to zero whenever there is no charge at that point, right? Everywhere, if at this point, what is that? I don't care what the electric field is anywhere, or how much charge. At this point, I don't see a charge. So divergence of the electric field has to be zero. Anywhere you don't see a charge, divergence of the electric field is zero. It has to be zero, right? Because otherwise there is a source of the electric field, and source of an electric field always a charge. So this is, if it is analytic everywhere, that's equal to zero. But now we will talk about situations where at one point it is not analytic, and that will be called a pole. Is that clear at this point? So instead of a charge, we will talk about a pole. Now, in electric field, there is a charge that contributes to the divergence of the electric field. Here, it will be the non-analyticity will come. We'll talk about special non-analyticity of that of a pole, and that will have some nice effects. Is that clear? Okay, so we want to talk about a pole then, right? Yes.
Yeah. I'm kind of confused on the del z star. Why is it zero?
Oh, I said if f is analytic, this is also analytic. If a function is analytic, because of Cauchy-Riemann conditions, this is zero, right? That was, if f is analytic, this has to be true. One way to say it is Cauchy-Riemann conditions is zero, but Cauchy-Riemann conditions is zero implies that this is equal to zero in a much more succinct manner, right? That was the first few steps. Yeah, here, right? So we said this is equal to zero, but this is equal to zero means this is equal to zero, right? Forget the integral. But these are individually zero because of Cauchy-Riemann conditions. Right? If this is zero, that's zero, that's zero.
That's how we got it. Yeah.
Yeah. So analytic function means Cauchy-Riemann conditions has to be satisfied. Cauchy-Riemann conditions means this is another way of writing Cauchy-Riemann. Cauchy-Riemann condition in terms of Z and Z star reads like this. And this is much more easier to see through. Right? If I either give you a function and ask you to verify this, it's much harder to see through as far as algebraically. Here, write it as a function of Z and Z star. And if there is no Z star, it's not like, for example, exponent logarithm of Z. Is it analytic or not?
Not analytic.
A log of Z? Okay. I mean, it's a hard one I'm giving. Is it analytic or not?
There is
Yes.
Z prime.
Does it have Z prime in it? Like analyticity requires that there should be no Z prime, right? Because if there is no Z prime, then this is satisfied. And this has no Z prime. So Cauchy-Riemann conditions are satisfied, right? So it is a very good guess that it is analytic, except that there could be some discontinuity. That one has to, and logarithm is a hard example in this case, that in the sense that it does not, it does satisfy Cauchy-Riemann conditions, but still there is some discontinuity in there. So which we will talk about. Okay. Did I clarify that?
Yeah.
Okay, so that's good. So let's now introduce. So again, just for Cauchy's, let's just state this. Cauchy's theorem states that integral C on a contour C f of V is equal to 0. If f of Z is analytic everywhere inside C. Like again, this is a pretty strong statement. You're saying that something happening on the edge of the universe is decided by inside the universe. You don't expect that, right? I mean, eventually, and that is a property of a continuous function. Continuous function says that this point decides the next point decides the next point, and if it is continuous all through, then you can reach infinity that way. So that's kind of the very naive way of looking at it. Okay. So let's introduce a single pole. Let's consider an example of Z f of I think so. F of Z. Let's say this is Z minus A. Let's also integrate this on contour C. Let's say this is a function of some integral, this function of A, right? It cannot depend on Z because after integration, the Z is gone. So it depends on the function on A. And A is some complex number. It's some complex variable if you want. Yeah, so how does this work? So let's say this is your complex function. This is your contour C. It has a sense of rotation, so that's your counterclockwise sense. And let's say A is inside that contour. It didn't have to be. I say that, let us say that it is inside the contour. We are saying that f of z is analytic everywhere. F of z itself is analytic. That means the only place it is not analytic is the z equal to a point. Like because there is a 1 over z minus a at z goes to infinity. So it just does not satisfy that. So that's your feature, and so that's your point A. But now how can I use analytic? So I say that this is contour C. I now break this contour into a circular contour that goes around this point and then goes back, right? So let's say I go here, I come here, then let me again go in the counterclockwise sense, and then I return back on the same path, and then I complete the whole thing. Is that clear? So I break the whole contour into, take a detour if you want, come here, go around the circle, and then I go back. Now, in this new way of seeing, I have a contour which is here. That's my new contour. So I can break the contour into two. Let's say this is epsilon, and let's say this is C and this is C1. So this is the same, or sorry, not the same. I should say that I of A surely is equal to 0 when I go from C plus C1. Like that, because that way I'm avoiding that analytic. So it is analytic everywhere in this shaded region. So this is true. dz of z of z minus a is equal to 0. This is using Cauchy's theorem. Is that clear? This is equal to 0 because of Cauchy's theorem. It is analytic everywhere. But this one we cannot say. But if these two are together correct, then I can say that C1 must be 0. Sorry, not C1 must be 0. C1 must be equal to IA. Is that clear what I'm saying? No. Okay. So let's try this again. So I of A, this is equal to 0. Okay. Let's start from here. I of A is equal to do the contour on C plus C1 minus C1. How about that? Z f of z minus. That's okay. Like I make a contour, I go on C1 and then go back on C1. I return back. So that's should be identical. I'm not changing anything. It's an integration. But now I split the two pieces. So this is the same as C plus C1 z f of z times z minus a, and minus, let me put the C minus C1 here, and this is plus C1. That's also true. But this one is equal to 0 because of analytic, so because of Cauchy's theorem. Because this is on a region, this is a shaded region. Right? So this is equal to 0 because of Cauchy's theorem. And this is what we'll keep doing this again and again. This is the basic idea of contour integration, that you want to isolate the contour, isolate the pole. You want to go into, even if it is not analytic, you isolate that non-analyticity to poles, and then we can talk about something in other places just because Cauchy's theorem. And we'll see at this point it's just this, right? Any questions here? And I'm going to evaluate this. This is just diagrammatic at this point, but I'll evaluate this function oh, is this 40? Oh, you guys are not telling me. You guys need to run. Okay, we'll do this later. I didn't realize how the time went. Oh, sorry. Yeah, you guys should run.